In this week, we will begin talking about Markov chain Monte Carlo methods. I remember when I collected the students' homework 0, there was a question on why are you taking this course? And some of the students indicated that they are in this course because they want to learn about MCMC. So finally, here it is. Let's begin with a recap of Bayesian inference. In Bayesian inference, our parameter of interest, theta, is assumed to be a random variable. Inferences under the Bayesian framework are based on the posterior distribution of theta given the observed data x. The posterior distribution, which is usually denoted by f theta given x, is the conditional distribution of theta given the observed data. This is equal to the joint distribution of theta and the observed data, which is given by the likelihood times the prior for theta, divided by the marginal probability of observing the data. The marginal probability of x's can be obtained on the denominator by integrating out theta from the joint density. And we know that this is proportional to the likelihood times the prior density. If we can draw samples of theta from the posterior distribution, then we can do everything we have learned in Monte Carlo estimation and Monte Carlo inference. We can get Monte Carlo estimates of parameters of our interest. However, here's the challenge. Drawing samples from the posterior distribution can be hard when the analytic expression for the posterior distribution cannot be found. In other words, there might not be a closed form expression for the posterior density of theta given x. This is where MCMC techniques come in. Markov chain Monte Carlo techniques construct Markov chain for theta, denoted by theta t, indexed by time, that are natural numbers. And for this Markov chain, the posterior distribution of theta given x is its stationary distribution. If this Markov chain theta t is ergodic, then theta t will converge to the posterior distribution. This allows us to set up the Markov chain and draw samples of theta so that it will get closer and closer to the posterior density. In MCMC, here are some of the general steps. At iteration t equals 0, that is the initial time point, we will first generate an initial value of theta, denoted theta 0. Then, at each subsequent time point, for example, at the tth iteration, we will generate theta t conditioning on theta t minus 1, which is the theta from the last iteration, according to some transition probability. Suppose that after a large number of iterations, say a total of large R iterations, the theta t has converged to the stationary distribution. That would imply that the theta t's after the rth iteration can be regarded as samples from the posterior distribution. This will allow us to treat all of these samples after the rth iteration as samples from the posterior, which will allow us to do Monte Carlo estimation and Monte Carlo inference. The question is, what transition probability should we use when we sample theta t conditioning on theta t minus 1? For this week, we will stick to the case that theta is one-dimensional. So we have a univariate theta, where theta is a single unknown parameter. And we will introduce a method called Metropolis-Hastings sampling algorithm. I might also call it the Metropolis-Hastings algorithm or the Metropolis-Hastings sampler or the MH sampler, but they are all the same things. The MH algorithm specifies how to generate theta t plus 1 given theta t. The resulting Markov chain of theta t's has stationary distribution, that is the posterior distribution that we're interested in. The MH algorithm provides a very flexible and popular method for doing Bayesian MCMC. One of the limitations it might have is that it sometimes can be quite slow. So if you have taken courses on Bayesian or you have used Bayesian techniques before, you might know that there is a software called Bugs. So there's one called WinBugs and there's an open source version called OpenBugs. And for a lot of the MCMC algorithms implemented in these packages, they actually rely on Metropolis Hastings sampling. We will introduce the MH algorithm this week, and next week we will introduce a Gibbs sampler. So the Gibbs sampler can be seen as a special case of Metropolis Hastings, and it is very useful when our theta is multidimensional, meaning that we have multiple unknown parameters that we try to estimate. Also, next week, we will talk about methods to examine the convergence of Markov chains in the MCMC framework, which will allow us to decide what is the number of iterations we will need to see whether the chain has reached convergence.